By 1945, with World War II finally in the rearview mirror after nearly 6 years of grueling combat, designing cutting-edge military aircraft was not exactly Britain's top priority. It was around this time that Roy Chadwick decided to think outside the box. He was the chief designer at Avro and Company, better known today as Avro. On a small scrap of paper, he sketched out a totally new passenger airliner. It featured a radical triangular planform, better known today as a delta wing. But by 1947, the global situation had drastically changed. The geopolitical ambitions of the communist bloc were becoming all too obvious. Because of this, Great Britain fast-tracked its own nuclear weapons program. Of course, to deliver those weapons, they needed a capable platform. They needed a cutting-edge, high-speed bomber. The government issued a specification, and the aviation industry immediately responded with a series of bold ideas. Two giants made it to the finals. These were Avro and Handley Page. Roy Chadwick tackled the creation of the bomber with incredible enthusiasm. This bomber was designated the Type 698. He was fully committed to the delta wing concept. Meanwhile, their competitors at Handley Page took a completely different approach for their HP-80 project. They decided on a crescent-shaped wing. In March 1947, the Air Ministry signed contracts with both manufacturers. The goal was to build 4 prototypes. This meant 2 aircraft from each company. Stepping into uncharted aerodynamic territory, Avro's management decided they needed a proof of concept. They wanted to figure out exactly how the delta wing would behave in the air. To do this, they initially planned to build a simple, unpowered glider of the same shape. However, Air Ministry officials showed some real foresight. They insisted that a proper, powered aircraft would provide much more accurate and valuable research data. This would be true even for a 1/3 scale model, so the ministry gave the green light to build an experimental airplane. The company designated this airplane the Type 707. Around the same time, the engineers drew up plans for another aircraft. This was a twin-engine, high-speed research plane called the Type 710. It was designed to study flight at near-sonic speeds. This target was around Mach 0.95. It was also meant to fly at extreme altitudes up to 59,000 feet. But after crunching the numbers, they realized the payoff just wasn't there. The marginal gains in data would not justify the massive investment of time and money needed to build it. As a result, they decided to scrap the Type 710 project. It never left the drawing board. Following the cancellation, the company received a new order. They were asked to build 3 different versions of the experimental Type 707 at once. One version was for high-speed flight and 2 were for low-speed testing. They decided to power each of these aircraft with the proven Rolls-Royce Derwent 5 turbojet engine. This engine produced 3,500 pounds of thrust. By September 1948, the factories were buzzing with activity. Workers began cutting metal for the very first prototype. The first Type 707 prototype was built for a very specific purpose. It was designed to gather practical aerodynamic data specifically for the upcoming Type 698 heavy bomber. It wasn't just a generic flying laboratory, it was a dedicated proof of concept for the 698. Because of this, high flight performance was not really the goal. The engineers wanted to save as much money as possible and speed up the assembly process. To do this, they decided to use off-the-shelf parts from other airplanes. These were parts from aircraft already in mass production by Hawker Siddeley. It was basically a parts bin special. For example, the main landing gear struts were borrowed from the Avro Athena trainer. This trainer had just entered production. Meanwhile, the clear cockpit canopy and the nose gear were pulled straight from the Gloster Meteor F-8 fighter. The first prototype rolled out of the shop in mid-August 1949. The aircraft was remarkably compact. Its power plant, a Derwent 5 turbojet, was tucked away in the tail section. A dorsal air intake sat right on the spine of the aircraft, split straight down the middle by the leading edge of the vertical stabilizer. It featured an all-metal airframe with a stressed skin construction to carry flight loads. The jet had a short nose that transitioned sharply into a broad delta wing. This wing had straight leading and trailing edges, meeting at pointed wingtips. To save weight, the cockpit wasn't even fitted with an ejection seat. It was also positioned extremely far forward. A long nose boom extended from the front of the aircraft. It carried air data sensors to measure angle of attack and side slip. As a failsafe, engineers packed an anti-spin parachute inside a small tubular fairing at the base of the tail. The pilot controlled this unique aircraft using a standard rudder and 4 movable surfaces along the wing's trailing edge. The outer pair acted as ailerons for roll control. The inner pair worked as elevators for pitch. For deceleration, the designers included a system of deployable dive brakes. 2 were located on either side of the tail cone just below the vertical stabilizer. 2 additional air brakes were tucked under the wing, right in front of the main landing gear bays. When the bare metal prototype, registered VX784, first rolled out of the assembly plant in Woodford, it sported a highly minimalist look. A national fin flash decorated the tail. It wore a large yellow letter P on the nose, marking it as an experimental prototype. However, traditional roundels were completely omitted from the fuselage. Before taking to the skies, engineers ran a thorough check of the systems and conducted initial taxi tests. On August 26, 1949, the aircraft was carefully dismantled. It was then trucked to the RAF Boscombe Down test facility. Here, preparations began for the most critical phase, which was actual flight testing. But the flight test program hit a snag immediately. Severe crosswinds swept across the runway at the testing center. Taking off in those conditions in a delta-wing aircraft was simply too risky. Its aerodynamic quirks were still a complete mystery to the engineering team. The crew endured over 24 hours of tense, frustrating delays. Finally, at 7:30 p.m. on September 4th, the winds died down. Avro's deputy chief test pilot, Flight Lieutenant Eric Red Essler, climbed into the cockpit. He took the small delta-wing jet up into the evening sky over Wiltshire. This completed a successful and historic first flight that lasted exactly 35 minutes. Over the next 2 days, Essler logged another 2.5 hours of flight time. This gave him a real feel for the radical new jet. He found that flying the Delta was just as straightforward as handling a standard straight-wing aircraft. However, it did require a slightly longer takeoff roll. By September 6th, Avro's management decided it was time to publicly debut their new aircraft. Essler flew VX784 cross-country to Farnborough. He arrived right in time for the annual Society of British Aircraft Constructors show. Parked on the ramp for static display, the unusual delta-wing design instantly grabbed the attention of the entire aviation community. After a huge success at the annual air show, the VX784 prototype returned to its base at Boscombe Down. The engineers used this downtime to install additional telemetry and measurement gear needed to capture precise flight data. By the last week of September, the intensive flight test program was back up and running. The delta-wing aircraft exhibited fantastic handling characteristics. It performed flawlessly for a solid 26 days of intensive test flying. That is exactly why the sudden crash on September 30th near Blackbush Airfield came as a massive shock. It stunned both the Avro design team and the personnel at the test center. Tragically, the crash claimed the life of their talented test pilot, Eric Red Essler. Investigators could not immediately determine the exact cause of the crash. However, they strongly suspected a fatal failure in the air brake control system. It appeared the mechanism had simply jammed. This locked the air brakes in the fully deployed position right as the aircraft was flying a low-speed, low-altitude test profile. As a result, the aircraft suffered a sudden loss of lift, stalled, and snapped into a steep dive. At such a low altitude, recovering the aircraft was physically impossible. In reality, even if the VX784 prototype had been fitted with an ejection seat, Essler's chances of survival would still have been incredibly slim. Early 1949 era ejection seats required significantly more altitude for a parachute to safely deploy. This was especially true compared to modern egress systems. The first VX784 airframe served as the baseline for the Type 707 family. Meanwhile, the second aircraft received the updated designation Type 707B. It carried the serial number VX790. By the time the first prototype tragically crashed, assembly on this second airframe was already nearing completion. Still, the sudden loss caught Avro's management completely by surprise. The engineering team had to scramble to rethink their approach for the second aircraft. The biggest takeaway was that integrating a reliable Martin Baker Mark I ejection seat had to be their absolute top priority. Every single lesson learned from the brief flight history of the first VX-784 was incorporated directly into VX-790. Because of this, on top of adding the ejection seat, the team had to design a completely new fuselage nose section. It was noticeably longer. They also had to totally redesign the canopy. The tail surfaces were also enlarged. However, the Derwent turbojet retained an intake configuration that visually mirrored the original Type 707. The engineers strongly suspected that the air brakes caused the VX-784 crash. Because of this, that entire system was completely overhauled. The old mechanism located in the rear fuselage was scrapped entirely. In its place, they implemented a brand new design. The upper air brakes were repositioned to sit flush with the wing skin. They worked in tandem with the underwing brakes that they decided to keep. At the same time, designers made some crucial adjustments to the elevator controls. It is worth pointing out that Avro was trying to save as much time and money as possible on this new airframe. Therefore, they sourced the nose landing gear directly from the Hawker Seahawk fighter. This fighter was already rolling off the production line. Ultimately, all these upgrades and adjustments significantly cleaned up the aerodynamics on the Type 707B compared to its predecessor. They also made balancing the aircraft's center of gravity much easier. The primary mission for the Type 707B was to closely study exactly how a delta wing behaves at low airspeeds. This program was highly valuable in its own right. It was not exclusively tied to the development of the upcoming Type 698 strategic bomber. During the last week of August 1950, the Type 707B made its way overland to the Boscombe Down test facility. The aircraft was painted entirely in bright blue and sported a noticeably longer nose section than its predecessor. Once it arrived, ground crews ran it through extensive system checks and a series of taxi tests. Reportedly, during one of these high-speed ground runs, the aircraft even accidentally lifted off the runway. All this meticulous prep work finally culminated in its first official flight on September 6th. At the controls was Avro's chief test pilot. This was the highly decorated Royal Air Force Wing Commander Roland John Rowley Falk. During his colorful career with the Royal Air Force, Falk had flown a wide variety of captured German Luftwaffe aircraft. He did this while heading up the experimental flying department, which evaluated enemy aviation. Even before World War II, during the conflicts in Ethiopia and Spain, Falk flew some seriously demanding missions for the British press. So by the time he joined the Avro team in 1950, he brought with him an incredible amount of flight experience and absolute nerves of steel. With the entire company's future riding directly on the success of this Delta Wing program, everything hinged on the flight data Falk was about to gather from the Type 707B. You can imagine the collective sigh of relief at Avro when Falk touched down VX-790 after a 15-minute maiden flight. He immediately radioed in that all systems were running perfectly and that the aircraft handled beautifully. This long-awaited news essentially breathed life right back into the company's managing director, Sir Roy Dobson. Along with Air Marshal John Boothman, he immediately requested to put this unique aircraft on static display. It would be shown at the prestigious SBAC Air Show, which was kicking off the very next day. Once they got the official green light, Falk took the aircraft up and headed for Farnborough. He flew the exact same route his colleague Essler had flown exactly 1 year earlier. This allowed the cutting-edge aircraft to be shown off in all its glory. An absolutely thrilled crowd got to see it by the end of the week. After wrapping up the static displays at Farnborough, the experimental prototype was handed over for a rigorous flight test program. On October 24th, the aircraft arrived at the test facility for a full evaluation of its flight envelope. It is worth noting that this was the first time the engineering team actually got to perform such a comprehensive shakedown. This was because the previous prototype had crashed before it could complete the required testing schedule. Test pilots loved it, and the innovative Delta Wing didn't throw any nasty handling surprises at them. However, when Falk pushed the aircraft through a speed range of roughly 100 to 410 miles per hour, a major issue popped up. They discovered that at high speeds, the dorsal air intake was practically starving the engine of air. Rolls-Royce stepped in to help. They offered up their wind tunnel for extensive aerodynamic testing. The tests revealed that the cockpit canopy was kicking up severe turbulence. This was completely disrupting the clean airflow right before it could enter the engine. In February 1951, they successfully fixed the flaw. Engineers significantly enlarged the intake. They also installed a dedicated duct to properly channel the boundary layer airflow between the cockpit and the engine. This prototype's takeoff roll was still almost as long as its predecessors. On top of that, the elevator lacked authority until the aircraft reached liftoff speed. To fix this, the designers had to tweak the aircraft's pitch attitude during the takeoff run. The solution turned out to be incredibly simple and elegant. They just extended the nose gear oleo strut by exactly 9 inches. Thanks to this small but crucial change, the angle of attack immediately improved. The aircraft needed significantly less runway to get airborne. Throughout 1951, this aircraft logged over 100 flight hours during intensive testing. It also put on its first major flight demonstration at a large public air show. That same year, engineers tested out a drag chute for landing. The setup worked so well that it was later adopted for the upcoming Type 6-98 strategic bomber. On top of that, some interesting experiments with tilting the jet nozzle proved successful. Vectoring the exhaust properly gave the aircraft much better overall stability in the air compared to a standard straight tailpipe. In September, right as the Woodford plant was starting to assemble the first parts for the Type 6-98 bomber, this research prototype was transferred to Boscombe Down. They were planning an extensive test program there to evaluate the stability of the delta wing. However, those tests had to be put on hold immediately. A serious accident happened almost right after the aircraft arrived. Extensive repairs took several months. It was not until May 16, 1952, that testing finally resumed. This allowed them to add another 30 valuable flight hours to the airframe's logbook. With that phase of testing successfully wrapped up, the 707B was on the move again. This time, the aircraft was sent to the Royal Aircraft Establishment at Farnborough. The jet served there for a few years. Then, on January 26, 1956, it was handed over to the Empire Test Pilot School. This facility was located at the very same base in Wiltshire. Unfortunately, its new operators were pretty rough on this unique aircraft. On September 29th, it suffered a hard emergency landing. An inspection board quickly determined that the airframe was beyond economical repair. Later that year, it was sent off for long-term storage at a military depot in Bicester. On October 22, 1957, this long-suffering prototype, still heavily damaged, made its final journey. It was trucked over to another facility in Thurley. This site was located on the grounds of the former USAAF 306th Bomb Group Base. In the post-war years, this location became known as the Bedford Research Center. That is where the story of this unique experimental jet finally came to an end. The battered airframe was simply stripped for parts to keep the third Type 707 prototype airworthy. Whatever metal was left over was scrapped for good. As mentioned earlier, by 1951, construction on the ambitious Type 6-98 bomber was in full swing. At the time, it seemed like building any more of the smaller Type 707 airframes was completely pointless. The designers had already gotten all the data they needed from the earlier experimental model. But the aerodynamics forced a change in plans. Wind tunnel testing on a full-scale mock-up yielded unexpected results. It turned out that moving the engine air intakes closer to the wing roots and slightly increasing the wingspan would significantly improve the aircraft's performance. To test this theory in the real world, Avro was given a new task. They needed to build a third experimental aircraft. It was to be fitted with the new wing root intakes. Its wingspan was scaled to exactly 1/3 the size of the upcoming heavy bomber. Due to a quirk in the designation system, this third aircraft was designated the Type 707A. The new prototype was identical in length to the previous version. However, it featured a slightly larger wingspan. Power came from a British Derwent 8 engine. This engine produced 3,600 pounds of thrust. Visually, this updated aircraft closely resembled the future Type 6-98 strategic bomber. The most obvious change was the removal of the dorsal fuselage air intake seen on earlier versions. Instead, it featured a new pair of intakes integrated cleanly into the wing roots. Assembly of this updated prototype was completed in the summer of 1951. From there, things followed a familiar routine. The aircraft was carefully transported by road to the Boscombe Down test facility. There, on July 14th, renowned test pilot Roland Falk took the aircraft up for its maiden flight. The experimental jet looked incredibly striking. It was painted entirely in bright red. Only the areas around the intakes were left in bare metal for technical reasons. Interestingly, the British Ministry of Supply believed from the outset that this third aircraft was a waste of resources. However, Avro management had much more ambitious plans for the project. They decided to press on and build a second Type 707A. This aircraft was built at a different factory. It was a separate facility located just south of Lincoln in the town of Bracebridge Heath. Typically, this facility only handled routine maintenance and major aircraft overhauls. But this time they were tasked with building a unique prototype. The location itself had a rich aviation history dating back to World War I. During that era, the factory assembled the famous Maurice Farman MF-7 Longhorn biplanes. The sky above the small local airfield was constantly filled with various Sopwith fighters undergoing testing. Production shut down in the 1920s due to a lack of orders. But the story of the factory did not end there. Shortly before the outbreak of World War II, Avro decided to revive the workshops. They converted them into a massive repair and storage base for the legendary Lancaster heavy bombers. These bombers were seeing heavy wartime use. Once completed, this new prototype was painted in the exact same bright red as its predecessor. However, its path to its first flight was a bit different. Royal Air Force Waddington was located just 2 miles down the main road from the factory. Because of this close proximity, they decided to simply tow the new aircraft to the airfield on its own landing gear. They towed it straight down the public highway. On February 20th, 1953, Avro test pilot John Charles Nelson successfully took it up for its maiden flight. This was exactly 20 months after the previous prototype took to the sky. It is worth pointing out an interesting paradox. The first prototype of the massive Type 698 bomber actually took to the air 6 months before this additional test aircraft even flew. By that time, the first red prototype had already been actively flying and undergoing testing for a full year. It proved the efficiency of the new wing root intake design. Also, by working alongside its newly built twin, it made a massive contribution to the final design of the bomber. Together, their flight data proved far more valuable than the efforts of all the previous experimental aircraft combined. The wings on both of these test aircraft were built to an exact 1/3 scale of the full-size bomber. This allowed them to replicate the aerodynamics and overall geometry of the upcoming Type 698 as closely as possible. But during the rigorous flight test program, pilots started noticing a troubling issue. A strange, albeit minor vibration would develop in the wings. This was something they had not encountered before during flights at moderate speeds. To make matters worse, with every additional knot of airspeed, this vibration grew stronger and more noticeable in the cockpit. On top of that, these severe vibrations worsened significantly as the aircraft climbed to high altitudes. Because of this unexpected problem, the massive development program for the Type 698 bomber was pushed to the brink of a major crisis. And this time, it was not the usual budget issues or minor aerodynamic miscalculations. The real threat was timing. The first full-scale prototype was already deep into actual flight testing. The second was in the final stages of assembly. Furthermore, the factories had already manufactured key components and sub-assemblies for an entire batch of production aircraft. If they could not cure the wing vibration quickly, all that massive effort and investment would be completely wasted. Extensive flight testing of the Type 707A confirmed a critical detail. The dangerous vibration was being triggered by airflow over the outer wingtips. Engineers immediately started looking for a fix. At first, they fitted aerodynamic wing fences to one of the test prototypes at about 3/4 span. This improved the airflow slightly, but it did not completely eliminate the vibrations. The aircraft remained unsafe to fly. The design team worked literally day and night. They eventually came up with a radical solution. This was a complete redesign of the wing's leading edge. They successfully tested the new geometry in the wind tunnel. However, the biggest hurdle was still ahead. This was actual flight testing. This new wing, dubbed Phase 2 by the Type 698 design team, looked noticeably different. They reduced the sweep angle of the leading edge from the wing root almost all the way out to the tips, but out on the outer wing sections, they actually increased the sweep. Viewed from above, the outer portions of the wings were now swept back much more sharply than in the original layout. This compound sweep was expected to completely change the aircraft's aerodynamics. To prove this theory in practice, they fitted a scaled-down version of the new Type 698 wings onto one of the test aircraft at Bracebridge Heath. When the aircraft finally took to the skies, the team could breathe a sigh of relief. The fix worked perfectly. The vibration completely disappeared across the entire speed and altitude envelope. But there was a catch. While the engineers had been racking their brains over the problem, the factories had not stopped production. They continued to churn out parts based on the original blueprints. As a result, they had to scrap 16 fully completed sets of the original wings. Some even had to be pulled off nearly assembled production aircraft. This cost a massive amount of time and resources. Looking back, it seems pretty obvious now that a problem of this scale should have been caught and fixed a lot earlier. The development program for the Type 707 test aircraft should have lined up perfectly with the production schedule for the Type 698 heavy bombers. But as they say, hindsight is 20/20. The main takeaway from this story was that the Delta Wing proved to be incredibly effective. This aerodynamic design was able to adapt to whatever technical challenges the era threw at it. This meant the decision to press ahead with the massive bomber program using this wing configuration turned out to be 100% right. Later on, the manufacturer was awarded a new government contract. This gave them the green light to build a second Type 707A. On top of that, the order called for the design and construction of 4 additional aircraft in a dedicated 2-seat trainer configuration. This training version was designated the Type 707C. The main idea was to safely and efficiently teach military pilots how to fly Delta Wing aircraft. These were still pretty unconventional back then. To make things work for both the instructor and the student, the cockpit was designed with side-by-side seating and fully dual flight controls. In August 1952, the first full-scale prototype of the Type 698 bomber successfully took to the skies. The second one had just rolled off the assembly line. Because of this rapid progress, the military asked a logical question. Did they really need 4 Type 707C trainers? Government officials figured that this many training aircraft was overkill, so the order for 3 of the planes was simply canceled. The sole remaining Type 707C on order had to be assembled at the Bracebridge Heath facility. The main Woodford plant was operating at full capacity with the full-scale production of the heavy bombers. It had no floor space left. Assembly of the single Type 707C trainer wrapped up in the summer of 1953. The aircraft was painted in a shiny silver finish. It was shipped off to Royal Air Force Base Waddington for a series of test flights. These trials kicked off on July 1st, with experienced test pilot James Barry Wales taking the controls. Sitting in the cockpit of this aircraft was quite a claustrophobic experience. They managed to squeeze 2 pilot seats into a fuselage that was kept just as narrow as the single-seat version. Because it was such a tight fit, there wasn't even room to install ejection seats. The space was so cramped that the pilots had to be on incredibly good terms just to share a flight. On top of that, the cockpit was enclosed by a heavily framed metal canopy. To get any kind of outside visibility, the aviators were left with just 2 tiny round windows. Just like the earlier Type 707A models, the heart of this trainer was the reliable Rolls-Royce Derwent 8 jet engine. This unique Type 707C first took to the skies over Woodford during factory testing, but by that point, the massive Type 698 bomber was already in full-scale production. This little trainer was practically late to the party. It couldn't really impact the development of the main project anymore. Despite all that, the Type 707C proved incredibly useful when it came to developing flight control systems for modern aircraft. For 14 straight years, this airframe was actively used for test flights at the British research centers in Farnborough and Bedford. Its main feature was its unique dual control system. From one seat, the pilot could fly the aircraft completely manually. From the other, they could fly using hydraulic boost or even electronic flight controls. This allowed engineers to directly compare 2 completely different piloting modes. It was exactly from these pioneering tests that the modern electronic flight control system, known today as fly-by-wire, was eventually born. By 1967, the research center had wrapped up its work with airframe WZ-744. The aircraft was then transferred to RAF Finningley. There, it joined another prototype, WZ-736. Over the years, the airframe made the rounds through a few other military bases. It spent time at RAF Cologne and Topcliffe. Today, though, after years of relocation, this historic aircraft has finally found a permanent home. It sits proudly on display at the RAF Museum, Cosford. Visitors can see it wearing its original restored WZ744 markings. Another variant, a Type 707A, bearing the tail number WZ736, also spent years contributing to flight research. It served as a testbed for cutting-edge auto-throttle systems designed for delta-wing aircraft. Because a delta wing requires a very high angle of attack during approach, pilots had to constantly chase the throttles to maintain the glide path. Handing this high workload task over to an automated system was much safer and more efficient. These critical flight tests wrapped up in 1967. After this, WZ736 was sent back to RAF Finningley for maintenance. Today, this bright red Type 707A still wears its original tail number. It stands out as a highly prized piece of the aviation collection at the Museum of Science and Industry in Manchester. But for WD-280, an airframe that played a major role in the second phase of delta wing development, things turned out quite differently. In the spring of 1956, up in Glasgow, the aircraft was carefully loaded onto the deck of the Royal Australian Navy aircraft carrier, HMAS Melbourne. After a 2-month voyage, it arrived in Sydney Harbour. From there, it was cross-decked to another carrier, the HMAS Sydney. This ship sailed straight for the city of Melbourne. But the adventure didn't end once it hit dry land. While crews were trying to move WD-280 on a specialized transporter, a metal support strut snapped under the aircraft's weight. Following this mishap, they had to scramble to find a much heavier duty transport rig. This was needed to haul the airframe to RAAF base Laverton. After being reassembled and put through a series of ground tests, the aircraft finally took to Australian skies in July 1956. For the next 7 years, right up until its final flight in 1963, WD-280 was heavily involved in numerous test programs. All of this research was spearheaded by the Royal Australian Air Force's Aircraft Research and Development Unit. This unit was known as ARDU. Over its service life down under, the airframe logged more than 203 flight hours. Later that same year, the British Ministry of Aviation decided to put the distinguished aircraft up for public auction. The winning bid came in at $1,000 Australian dollars. It was placed by an engineer named Geoffrey Mallet. That summer, the aircraft was transported directly to his property in a Melbourne suburb. Driven by his background and a deep passion for aviation, Mr. Mallet poured countless hours of meticulous care into the airplane. He completely repainted the airframe several times over the years. It wasn't until 1999 that WD-280 finally left private hands. It was relocated to the RAAF Museum in Point Cook, Victoria. There, it remains carefully preserved to this day. Throughout their service life, the story of these aircraft was closely tied to their big brother, the massive Type 698 bomber. One of the most unforgettable moments for thousands of spectators was their demonstration flight at a major airshow in 1953. Up in the skies over Farnborough, 2 all-white prototypes of the legendary Vulcan bomber flew in a stunning formation. They were escorted by 4 Type 707s, a silver 707C, a deep blue 707B, and 2 bright red 707, as made for an absolutely incredible sight. This historic flight became an iconic moment. It perfectly captured one of the most exciting eras in the rapid advancement of British aviation.